Hi everyone, I'm Samuel from CNSD. In this video, I will review some joint works with several collaborators on hyperparameter selection. I will especially focus on parameter selection using a technique called algorithmic differentiation, in other words, automatic differentiation. Our starting point is a collection of estimators W theta indexed by a parameters page denoted here, big theta. Okay, so we are in the parametric statistic world. To be more concrete, imagine that you have some noisy monkey and that you wish to remove some part of the noise, but without degrading it too much. One solution, among many others, is to use the so-called total variation regularization introduced by Fadili in the 90s. This method uses parameters that must be fitted to allow a good recovery. Indeed, depending on the value of this parameter, you may remove not enough noise, as you see here, or you may destroy too much details as you increase it. So the issue is how to choose such an hyperparameter. I will allow myself to speak about parameters instead of hyperparameters depending on the context. More formally, when one aims to solve a linear regression problem which is underdetermined, okay, so you have some observation y, which is the realization of x on the ground truth w true, okay, plus some noise. A typical way to solve such a problem in machine learning, in statistics, or even in signal processing is to use regularization, or DSA otherly, variational methods. Okay. Variational methods aim to make a trade-off between a data fidelity term, okay, and some regularity assumption which is on your estimate W. Okay. And this trade-off is typically done by using a parameter or several parameters theta. What is the most well-known problem which fits this case is the lasso introduced by Shendono or Tepshirani, which seeks to minimize both a least square term, okay, like ordinary least square, and a L1 penalization, which promotes sparse vector under some hypotheses. So, we have estimator, we have hyperparameter, and we want to select it. How to do it? One way is to say that we wish to have a criterion, okay, going from the parameter space to R, and taking an optimization point of view, our goal is to find the best parameter, okay, best hyperparameter, with respect to this matrix or this criterion, okay? Or at least, maybe not the best one, or one of the best, but someone which is close to this minimum. So, looking at it like this, what we have, if we go back to our monkey, is some criterion here, some risk, okay, some curve, and you can evaluate the risk associated to the solution of your estimator for several values of your parameter. And what you aim is to have the solution, the green solution, or at least something close to it. In inverse problem, a typical criterion is the estimation risk, which was introduced by Rice. The idea is to say that you take the expectation with all possible noise on your data, okay, between the mean square error, okay, between your estimator, your parametric estimator, and the ground truth. In machine learning, another point of view is the criterion is holdout loss, which is given a validation set, you aim simply to minimize the mean square error of your estimator on this validation set. Several other options exist, such as the projected risk, cross-validation, some model criteria, and so on. So, given this criterion, probably the most basic algorithm to choose the good parameter, good hyperparameter, is to use what we call the grid search. The idea is the following. Choose a criterion here, okay? Then sample uniformly your hyperparameter space, then evaluate the criterion on this grid, and simply keeps the best theta star. This is absolutely the standard in machine learning implemented everywhere, from R to Python to every paper. But there is a real dimensionality issues when you sample this parameter space, when you have more, for instance, more than one parameter, or when evaluating this risk is difficult. for instance, the estimation risk. The problem of dimensionality can be mitigated using random search or Bayesian methods, but this is not the focus of this talk, as we already said. Our focus is to look at hyperparameter selection as a first-order problem. Okay. So on, we will use first-order methods. So the goal is to solve a minimization problem. If we look at this criterion R as a composition, in fact, of some cost function associated to your estimator, we can say, okay, that this is a function of theta, okay, a bit more complicated to define, where the cost function goes from the scenario space to R, and your estimator goes from the parameter space to the scenario space. Assuming that this cost C and your estimator is differentiable with respect to theta, the gradient, okay, the gradient of this criterion can be simply obtained using the chain rule, meaning that you apply the transpose of the Jacobian to the gradient of your cost. And finding the best theta amounts to solve a saddle point. At least finding a saddle point amounts to solving this Euler equation. Using this formalization, what we have is that we need to perform a hypergradient descent, where each iterate is simply a descent with respect to this energy. It can be also projected gradient descent, since the parameter space typically is not unbounded. There is several potential issues with this formalization. What about the differentiability of C and the cost and the estimator? Do we really have access to the cost? That was not the case, for instance, for the estimation risk. The size of the Jacobian might be prohibitive. Also, this estimator, this theoretical estimator, is in fact typically obtained using an iterative estimator, which is not exactly this thing. Does this gradient estimation is stable with respect to approximation of our estimator? And lastly, what about the convergence of the hypergradient descent? It's typically non-convex, so what are the guarantees? So if we go back to the grid search, we can see it as a zero-order problem, okay, where we simply evaluate our function, whereas the gradient descent is a first-order problem, okay? And it's quite easy to convince yourself that in some situation, taking advantage of the information of the gradient will be helpful. So, given a differentiable estimator, we have to manipulate this object, this Jacobian. I just want to introduce a notation which will be important in this talk, which is the Jacobian, okay, with respect to the observation, okay, which is an application which map Rn, the observation space, towards the matrix space Rp times n, and the Jacobian with respect to the parameter, here the first one, which goes from the parameter space to the matrix space Rp times R. Okay, so when your Jacobian goes, okay, the Jacobian is a matrix goes you have only one. For instance, parameter, you really just have the transpose of a gradient. Okay. So, how to obtain this Jacobian or matrix of partial derivative? So, one way is to use simply a numerical approximation, which can be forward, backward, or center. Okay. But the idea here is that you will need at least a big O of nt operation, n being the parameter dimension of the observation space, and t being the cost of evaluating your estimate. Okay. So it can be prohibitive, okay, because if you take a precision which is too small, you will have something like a round of error, okay? It's well known in numerical analysis. And obviously, if you have a precision which is too small, you will have a truncation error, meaning that you will not get a good approximation of the derivative, okay? So unfortunately, it can be unstable for low and high precision, depending on the context. So another way to look at it is to use symbolic differentiation, which is something that many mathematicians use when they, for instance, use software like Mathematica, Mapper, SymPy, Maxima, some Lisp dialect. The issue is that for complex program, typically iterative one, you have it's quite inefficient and leads to what we call expression swell, where you cannot factor sufficiently your differentiation part. So what can we do? What can we do? I will introduce you algorithmic differentiation in a moment, but first I have to be a bit more specific, and I will talk about a very interesting criterion, so the prediction risk, and the associated estimator to it, which is the sure. Okay, so this is a work I did a few years ago now. So going back to the goal of finding our parameter, okay, in inverse problem, typically what you are interested is the estimation risk, which is the expectation with respect to the noise of the mean square error between your estimator and the ground truth. It is quite unlikely that we have access to this thing, and something which is a bit more reasonable maybe is to say, what if I know the noise? Okay, why not if it's small? Okay, maybe you can have access to what we call the prediction risk, meaning the mean square, the expectation of the mean square error, but after the action of your design matrix X. Okay. So first thing, not that typically, for instance, in imaging, you only have one observation Y, so this expectation is not computable. We'll see how to deal with that. And also we have access only to observation Y, and obviously the ground truth is not known. So what can we do to have access to this quantity? So a solution is called the Stein unbiased risk estimation, also called the SURE. Okay. So in this inverse problem context, you can define the prediction to be mu hat of Y, okay, which is simply the action of X on your estimator. Okay, and the prediction risk is a mean square error between this prediction and XW true. So in many statistical settings, we use something known as the degrees of freedom, introduced in the statistical literature by Bertrand in 1986, which is simply probably the sum of all covariance between your prediction and the observation, okay, with some scaling factor linked to the noise level. So this is something which appears in many model criteria. For instance, the speed of mallows, A, peak, the generalized cross-validation, the SURE, and so on. To have an insight of what is the degree of freedom, for instance, if you take the ordinary least square, it's really like, it's quite naturally leads to P, okay? Meaning that every covariate can independently move around, okay? If you look at the lasso, you can prove under some technical assumption that in fact the degree of freedom is nothing more than the L0 norm or the size of the support of your lasso estimator. So what is important is that the Stein lemma tells you that if your prediction is in fact a weakly differentiable estimator, then the empirical degrees of freedom, which is defined by the divergence, okay, trace of your Jacobian, okay, is in fact an unbiased estimate of the true degrees of freedom. And the Stein unbiased risk estimation, the SURE, is that under the same hypothesis of weak differentiability, the SURE, which is the mean square error between your observation and the prediction, with a corrective term depending on the noise level, plus this degrees of freedom, give you an unbiased estimator of your prediction risk. The small issue here is that it requires the knowledge of the noise variance, which is a challenge by itself. So if we go back to the for instance, the regularizer least square, okay, and the smooth case. So you have the original least square plus some regularization term, which is supposed to be smooth. Then you can easily write the first order condition, okay, which gives you the gradient of the least square plus theta times the gradient of your regularity term, okay. And if you use the implicit function theorem, okay, what you have is that this matrix derivative of what appears in the first order condition give you the Jacobian of your prediction, okay? But you have to take the inverse of this gamma theta function, okay? When you are not smooth, things are a bit more difficult, okay? But we proved with several collaborators that if J is regular enough, so for instance, the L1 norm, nuclear norm, slot norm, whatever, this Jacobian is in fact computable almost everywhere in closed form, which generalize a long series of work. So just to give you an insight, okay, you can use the Shure to do some grid search, okay. Here we use an anisotropic total variation, meaning that your regularization is a linear operator times W, but using the L1 norm. We took X to be a Gaussian convolution, okay, so it's give you a blurry and noisy image, okay. And if you look at the prediction risk, okay, which is the black dotted line, it typically fits very well with this closed form Shure, where when you are close to the optimal solution. Okay. The issue is that what I didn't tell you here is that we put under the carpet several issues, which is problem one, what you have is like expectation versus realization. So this is mostly stable because the expectation of a low dimensional quantity with a high dimensional variable. Okay, so it's not such an issue. You have the computational tractability. In fact, we didn't compute the true Jacobian. Okay, you have to take the trace of the Jacobian, but we use what we call the Monte Carlo Shure. I will introduce it in a moment. And the last problem is that what we did to compute this total variation problem is to use an iterative algorithm, which typically converge to the model one. So this one, you can compute the Jacobian using, for instance, the Monte Carlo Shure, okay? But what about the convergence of this iterative Jacobian towards the true Jacobian? And to have something which is meaningful, you need very high precision, okay? So if you remember, the DOF of the lasso, for instance, was the L0 norm, meaning the side of the support. So if you didn't have such a high precision, you don't estimate correctly the support and everything collapses. In order to overcome these issues, okay, we developed a technique based on forward automatic differentiation that we call sugar, which allows you for someone to estimate the Shure and to estimate also the gradient of the Shure. Okay, so let me explain what I mean by forward automatic differentiation and gradient of the Shure. So, as we said, the shortcomings of the Shure is the following. Okay. From a theoretical part, okay, what we have is a true mathematical estimator. Okay, and to derive the Jacobian of this estimator, what you have to do is to perform a sensitivity analysis. What we did, for instance, the theorems that I said, which encompass a large class of non-smooth problems. Okay. But on the practical part, okay, what you have is a numerical algorithm, an iterative one, and eventually you can have the Jacobian of this numerical algorithm. And everything here is not commutative, okay, for instance. You have to be extra careful because the convergence of the function, okay, does not imply the convergence of the derivative. Still, we will focus on how we can estimate the Jacobian of a numerical algorithm. Okay, so as I said previously, one way is to perform numerical approximation, forward difference, okay, or to use symbolic differentiation, which have the shortcoming of the expressions well. For numerical approximation, we have the problem of unstable for low and high precision. So I have now to introduce what is automatic differentiation or algorithmic differentiation, and especially the forward mode. So consider a function f here, and what you want is to estimate the Jacobian. Okay, so here I took a function from R3 to R2, okay, and I want to evaluate, for instance, the partial derivative of a function with respect to the first variable at some point, let's say 1, 2, 3. Okay, so I can do it by hand, it's quite simple. But how can I do this? How can I do it on a computer? So the automatic differentiation point of view is to say, okay, so forget about the function, we look at the computer program. Okay, so one way, okay, is to look at the program for here, written in a pseudocode like Python code, okay, and you can move this computer program towards some computational graph, okay, meaning that you have a directed acyclic graph which gives you how to compute your function, okay? So really, it's just reading your code in a linear way. Along with this computer program, you can write what we call the forward tangent program, which is in fact the derivative line by line of this program. So, for instance, to be a bit more concrete, if you want to estimate the partial derivative of f with respect to the first variable, what you will give to the forward tangent program is as input 1, 0, 0 to explain that it's really only the first variable that you want to obtain. Okay, so the first line was to say that you want to multiply x1 by times x2, okay, and the multiplication for in the derivative world is simply the sum of the derivative with respect to the first variable and the derivative with respect to the second variable. Okay, so you stack this value. Next, the second expression was taking the exponential of the last parameter. Again, here what you need is simply to derive the exponential. Okay, that's what you get. Give you 0 here because the input was 0 for the x3, but still it's this quantity. Same thing for the logarithm in base 10 here. So, okay, so you just obtain the derivative of the log. Okay, very good. Next, what you have is that you have an addition between the first variable v1 and v2, and the derivative is simply the sum of the derivative. Same thing for the difference. And what you output is this couple v4, v5. I have several commands here. So the first thing here is that, as we said, we obtain the derivative with respect to the first variable. Okay. Note that computing the full Jacobian, in fact, requires p calls to this tangent program. So if your parameter space has a huge dimension, it can be an issue. Second thing is that you move, okay, the computational graph from what we call, say, to the left to the right, okay? So there is no memory requirement, okay? You do not have to stack all the variables from the forward trace of your computer program. It's quite performant, in fact, when p is smaller than n, and was introduced first in the 60s, okay? So when you heard about forward automatic differentiation, it's the same thing as saying that you accumulate the numerical derivative, okay, in a forward way. In the automatic differentiation community, it's also called the tangent linear mode. From computer perspective, programming perspective, as you see, it's like line-to-line derivation. And from a mathematical point of view, what you estimate is in fact the Jacobian vector product. So for instance, if you want to obtain the trace, it's quite easy. since it amounts to put 1 for each variable. And you must have in mind that automatic differentiation is quite hot at the moment in the machine learning community under the name backpropagation. And the backpropagation is a reverse mode automatic differentiation that I don't need to introduce for this talk, but which can be seen as a counterpart of the adjoint linear mode of automatic differentiation. Note that in practice, the forward tangent program needs to be implemented in the same function as the original computer program, for instance, using an autograd engine or doing by hand. Okay, either it's just some pseudocode looking like Python. Okay, it's just pseudocode. Okay, so in our case, typically what we have is not any kind of estimators. Okay, we have something which is an iterative estimator, meaning that you have, for instance, gradient descent, forward, backward algorithm, and so on. Okay, so you can look at it as a sequence, WK, okay, which is a function of the parameter and the observation. Okay, and this sequence converges to the true estimator. Okay, one, for instance, the Lasso, okay, the optimization problem. Okay, and the properties is that to obtain the next iteration, you apply typically an operator T, going from the parameter space times the observation, okay, to your signal space. Okay. So this is a specific case of what we discussed just a slide ago. Okay, and the computational graph here is just a straight line, okay, where you apply T at each time, okay, and each time you forward this Y or theta block. Okay, so when you have this computational graph, you can apply the chain rule to it, okay, and you say that the Jacobian of the next iterate with respect to your parameter or the observation is what? Is the partial derivative of T with respect to the first variable, okay, apply to the previous iterate, times the previous Jacobian, okay, plus the derivative with respect to the second variable, which is the observation or the parameter. Okay. And with using this chain rule, what you can have is a forward differentiation of an iterative estimator, okay, the Jacobian vector product, meaning that in your code you still have the fact that you apply an iterative estimator, an iterative scheme, okay, and you apply at the same time the fact that the Jacobian of your estimator at k plus 1 is just the chain rule applied to the previous vector. Okay. So to be just a bit more specific on what happened really. So if we go back to the Lasso, for instance, okay, so the Lasso, it can be solved using an iterative soft thresholding, okay, also known as a forward-backward scheme in optimization community, okay. And in this case, what you have is that the next iterate is just the application of a proximity operator, okay. So if you don't know what is it, it's not very important, but at the moment, apply to a gradient step to the previous iterate. Okay, and what you have to is that if the step size of the inner gradient descent is well chosen, you have convergence of the sequence of iterates towards the origin, the true estimate. So this proximity operator is in fact what we call the soft thresholding. Okay, so you can soft thresholding in contrast to hard thresholding, the natural one, but which is discontinuous, okay? And this object can be derived with respect to the argument and give you the derivative, okay, of the absolute value. And if you do it coordinate-wise, you obtain a diagonal, the Jacobian matrix, which looks like a step. Okay. So more precisely, you can really write down explicitly the Jacobian of the soft thresholding with respect to the first variable, which is this diagonal Jacobian applied to your gradient descent times the Jacobian of the gradient descent, meaning simply identity minus tau and the grammar matrix, and the derivative of with respect to the second variable, and in this case, it's still the first part, this diagonal matrix, but this time times only the step size times x. Okay, so it gives you some way to compute the derivative of each estimate. Okay, but you don't have to stack them. You can just keep the last one, which should be the closest one to the true Jacobian. Okay, so now what we want, okay, is to be able to derive the sure, okay, in order to do a first order method. Okay, so going back to what I presented to you a few minutes ago, we have the closed form sure. Okay, if you are able to compute the estimated degrees of freedom, okay, you have the sure, which is the mean square error minus this corrective term plus the degrees of freedom, okay, and the degrees of freedom is only the trace of the true Jacobian. Okay, so the problem here, particularly, is the dimensionality of the Jacobian. Okay, so this is a huge thing. Okay, but what you can do is something we could call it a trick, is to use what is the Monte Carlo sure, and you have still this sure formula, but instead of computing the trace of the Jacobian, what you do is that you take a random vector, more precisely a normal vector, okay, and you compute the inner product between this Jacobian, okay, apply to z times z, meaning that you never have to store the full Jacobian, okay, you only need to apply it to some random vector. Okay, and the nice thing is that in expectation with respect to z, okay, this thing is an estimator of the estimated degrees of freedom, which itself is an estimator, an unbiased estimator of the degrees of freedom. Okay, so the issue is we did some forward differentiation, that we don't have access to the true Jacobian, only to an iterative one. Okay, so what you can do, that was a sequence of work, is to combine this iterative idea with the Monte Carlo. Okay, and so what you do is that you still have this sure formula, but instead of looking at the prediction, you look at the iterative prediction. Okay, and the iterative degrees of freedom with Monte Carlo techniques. So in fact, when I defined previously this derivative of the iterative scheme, you just have to take the inner product with respect to a random normal vector. Okay. The issue here, obviously, is that you need to prove the convergence of this quantity towards the first one. It's linked to the idea that an alternative to this iterative differentiation idea is to go back to finite difference methods of approximating a Jacobian. Okay, so I stop writing the full sure. Okay, so let's just keep the degrees of freedom in mind. Sure is quite obvious to derive from it. So the idea of finite difference sure is to say that instead of looking at the Jacobian, okay, we are going to look at some finite difference version of it. Meaning that, for instance, for the original FD sure, what you have is that you sum, so to take the trace or the divergence, if you want, you sum the forward difference between your estimator at y plus some perturbation, okay, along an axis, minus the one you want to obtain, okay? So if your estimator is Lipschitz continuous, you can prove easily that the limit when the step size go to 0, okay, of the finite difference sure converge to the true degrees of freedom. Okay, nice. The issue is that, okay, so you have the numerical instabilities potentially, okay, and you have this observation dimension, which could be an issue. So what you can do again is to use the Monte Carlo sure trick, okay, and you get in this case the FDMC sure, okay, meaning that instead of summing along all axes, what you do is you take a random normal vector and you look at the forward difference of your estimator with this normal vector. Okay, and in expectation with respect to z, this degrees of freedom of DMC is equal to the finite difference sure, which itself, when you take the limit, converge to the degrees of freedom. Again, you don't have accessibility to the true estimator, so what you can do is to look at the iterative finite difference Monte Carlo sure, which is exactly the same thing, but instead of looking at the true estimator, you look at the estimator, at your iterative estimator at some iteration k. And still, you have the issue of convergence of the derivative when the estimator itself converges. Okay, so let me just remind you something. So zero-order optimization can be, for instance, be described as a grid search. Okay, when you don't take advantage of your gradient. First order is this hypergradient descent. So, well, you choose a criterion, you take the starting point, you evaluate the criterion, so here the sure and the gradient on the fly, and you keep the last iterate. Okay, but we have a slight issue here, is that even if your risk here, okay, the estimation risk or the prediction risk can be weakly differentiable, it does not imply that the sure itself is differentiable or even continuous. Okay, so that's really an issue because obviously you don't have access to the prediction. Okay, but at least if you are able to compute the sure, you could expect that it has the same regularity as the estimation or the prediction risk. But that's not the case. Okay, but here we don't want to play with the sure. We want to play either, for instance, with the forward finite difference sure or the iterative finite difference Monte Carlo sure. And the good news is that if you assume that your estimator is weakly differentiable with respect to y and theta, okay, then given any step size, these two empirical degrees of freedom are also weakly differentiable. Okay, and so does the sure. And this idea gives birth to what we call the sugar, which is the Stein unbiased gradient estimator of the risk, which is simply the gradient of the sure of the finite difference or the finite difference Monte Carlo sure. Okay, so for instance, if we keep focused on only on the finite difference, okay, you show that applying the chain rule, this gradient is nothing more than the application of the Jacobian to the derivative of the mean square error plus the derivative, the gradient, sorry, of the degrees of freedom. Okay, and this degrees of freedom is simply computed by looking at finite difference of the Jacobian itself. Okay, so here it's not the estimator, it's the finite difference of the Jacobian. So it's something which is of order 2. Okay, so for the FDMC, it's exactly the same idea, but instead of looking at the sum, you take the inner product with a normal vector. And nice thing again is that if you assume that it's not only weakly differentiable, but the estimator is Lipschitz continuous with respect both to the observation and the parameter, then when the step size go to 0, in expectation, the sugar is the gradient of your prediction risk itself with respect to the parameter. So in practice, to have numerical stabilities, you should have the step size over the dimension of the observation space. It should not decrease too quickly because otherwise you have this round of error that we discussed at the start of the talk. Okay, so if now we go back to the iterative estimator applying the chain rule, what you can look is that in fact this equation of the sugar can be defined simply at looking at an iteration k, okay, as this iterative estimation of the Jacobian, okay, at some point y plus the step size, okay, applied to your normal vector, minus where you try to evaluate it. So as you can look, okay, the original algorithm was just an iterative thing, meaning that you have wk plus 1, which is equal to twk. Okay, so say that it has a cost, a given cost. Next, you need to estimate the derivative. Okay, so mainly it's the same cost you can expect. Okay, if the derivatives are not too complicated, it's the same cost as the original estimator. So you have running time times 2. Okay, now if you look, you need to evaluate all this estimator at y. Okay, but also at y plus delta z. Okay, so the running time is also multiplied by 2. So the overall cost is 4 times the original iterative estimator. It's both a lot, because it's 4 times slower, but it's also a fixed price to pay, which is absolutely not the case for other methods. Okay, so we generalize this sugar thing to several applications. So for instance, if you are not interested only by the prediction risk, but you have some assumption on the design matrix, we can have access to the projection risk or the estimation risk when the gram matrix is not singular, simply by looking, instead of looking at the prediction minus the xw true, you can apply any interesting matrix A in front of it. Okay. Another line of work that we did quite recently is to not look only at what happens with Gaussian noise with a diagonal matrix, okay, but with any kind of correlation matrix, which was very important for an application in texture segmentation. So we also have open problems. So for instance, what happened with non-Gaussian noise? For instance, can we adapt the sugar to Poisson noise, things like that? And what happened when you don't have non-weakly differentiable estimator, for instance, discontinuous one, but nicer, a bit nicer also? Can we derive some heuristics, some theory? So that's some open questions on this problem. So in practice, it works really well. For instance, let's look at total variation deblurring, that problem, the one that I introduced initially. So here what you do is that you minimize least square error, okay, with your observation, plus 2D TV regularity, isotropic one, meaning that you look at the L1, L2 regularization of the gradient of W. Okay, so that's a typical TV for imaging. And you compute it with a primal dual algorithm, so more specifically the Chambol-Pock method. And you do the differentiation that I proposed earlier. Next, what you do is the gradient descent, or more specifically quasi-Newton descent of the sugar to estimate theta. And what you can see on this different curve. So on the right, what you have is the original image, Y is a blurry image, and the last one is the obtained TV with the optimal parameter with respect to the gradient descent. Is that around the optimum, which is the red cross, what you can see is that the risk, the projection risk, and the sure estimated by iterative differentiation coincides. Okay, so that's not the case everywhere. If we dezoom a bit, okay, and you can see it's not really differentiable. Okay, it's not even weakly continuous at some point. Okay, but at the optimum, everything coincides quite nicely. So it makes sense to really use the sugar to try to optimize the original sure, okay, with a smooth counterpart. And if you look really at what happens when you run BFGS on this problem, in 4 iterations, okay, we obtain something which is quite nice, starting with an initialization not too far away. Okay. So we can do something similar, for instance, with multi-scale compressed sensing, where you replace the 2D isotropic TV with some wavelets transform. So if you are not familiar, it's like a Fourier transform, but which took into account the multi-scale aspect of imaging. Okay, so it infers smooth image, but also sharp discontinuities. Okay, and here what we did is to take 3 levels of it. So here J is equal to 3. Okay, and we did 3 tests. So the first one is to take only 1 level. The second one is to take 3 levels, but to fix 1 parameter fixed for all levels. And the last one is to use 1 parameter per level. Okay. And so the problem when I say compressed sensing is just that matrix X here is not a blurring, it's a Gaussian measurement matrix where the number of observation is way lower than the number P of pixel. Okay, and we use the same primal dual algorithm, the Chamberlain-Poquelin. So what you can observe, okay, is that indeed using more parameters improve the image. Okay. And what you can look is that the sure really leads to optimal parameter in terms of mean square error. Okay. So that's it for the sure. But initially, focus was to speak about different type of criteria. Okay. So I want to present a way which is more direct and using the sure, which can be applied, for instance, in machine learning when the criterion itself is the holdout loss. So just to remind you, our goal was to find the optimal parameter with respect to some criterion. Okay, this criterion itself can be rewriting as a cost applied to your estimator as a function of the parameters of the parameter. Using this chain rule, you can derive the gradient of this risk as only the application of the transpose of your Jacobian with respect to the parameter to the gradient of the cost applied to the estimator. And with this, you can apply an hypergradient descent to this risk. Okay. And you add this distinction between 0 order and one first order method, which is the gradient descent. Okay. So if you are in the setting where, not unlike the sure, where C is easy to compute, but the gradient itself is also easy to compute, that you have a variational estimator, okay, and that in fact you can see this variational estimator as the minimization of a convex smooth function. So in this case, you can look at the bi-level optimization problem, which is you look at finding the best parameter of this cost function, subject to the fact that your estimator itself is a solution of a variational problem. Okay. In this case, okay, with rewriting the gradient equation, okay, the chain rule, you have a fixed point equation, which is the fact that the gradient with respect to the first variable of your inner problem is equal to the other equation. So this is really a setting which is quite known for the smooth case since a long time. Okay, well, for instance, for kernel-based, weight switch, image restoration, noisy stability issue. Okay, and it was also a bit studied in the non-smooth case by several authors. Okay, now if you derive this first fixed point equation, okay, you obtain something which could look like an implicit function theorem thing, and assuming the invertibility of the Hessian, okay, you can rewrite the gradient of your estimator, the one that you want to obtain, as this product between partial Hessian. Okay, and still you have to invert this P times P system. Okay. So now when you are in the non-smooth case, if we focused, for instance, on the lasso, okay, so as we saw for iterative estimation, you can look also at the lasso as a solution of a fixed point equation, okay, which is for each coordinate you're trying for any positive alpha, okay, as this proximity operator applied to the gradient step, but only on one coordinate, okay? And this fixed point equation gives birth to what we call the proximal coordinate descent introduced by Sen, which is you iterate for the number of iterations that you want, you iterate each coordinate, okay? You take, for instance, we can also use random sketching or things like that, okay? And in this case, you update only your coordinates by saying that you take the 1D prox of this restricted gradient descent. So if you derive this fixed point equation, what you obtain, what you can prove, is that in fact the Jacobian of this of your estimator with respect to theta is split in two parts. Okay, the first part is the one on the support, where it satisfies this affine implicit affine equation, which is well known, and on the co-support, on the complementary of the support, you have the Jacobian, which is 0, which allow you to compress the storing of the Jacobian, which was the idea of the paper, the ICML paper that we did this year. Okay. The issue is that you have the Jacobian size that you can leverage with this observation, and you also have to inverse this matrix, even if it is defined, it's not said that it is well conjugate. So again, an idea is to say that instead of trying to solve something which is based on implicit function theorem at the end, okay, what you can do is to derive this proximal coordinate descent to estimate the Jacobian of your estimator, but this time with respect not to the observation, but to the parameters. Okay, so I won't describe precisely what we did to compress the Jacobian, okay? But I let you see the talk by Quentin on the ICML website. But I just want to describe a bit the numerical results, okay? That we obtained for the hold-out loss and the lasso. So mainly, we compared the implicit forward iterative differentiation, which was the algorithm that we proposed, and the implicit, the forward iterative, the one that I just introduced, with the implicit, so the one where you have to store everything, some grid search, some Bayesian optimization, the random search, and also the lattice one. Okay. So if you look consistently, the implicit forward iterative, the green curve, and the forward iterative, okay, which is the pink one, the bullet one, are very good contender to the more organized, for instance, implicit or grid search. Okay, we really have both in terms of objective function on the loss on the test set and with respect to the relative MSU, where the Bayesian is way slower. Okay, we always have something which is quite competitive. Okay. So let me summarize a bit this video. We have some estimator, okay, some parametric estimator by some parameter space, theta, okay? And our goal was to look at this parameter selection as an optimization problem, okay? Meaning that we aim to minimize some criterion leading to the best parameter, or something close to it. Using this, the remark that most of the time you don't have access to the true estimator, so for instance the lasso, but only to an iterative estimation of it. So for instance using the iteratives of threshold algorithm or forward backward for the lasso. I gave the idea that instead of looking at the first order information of the true estimator, what you can do is looking at the first order of the iterative estimator itself and doing it online, meaning that you compute the Jacobian of this iterative estimator at each step, okay, using the chain rule. And when you have access to it, you can do an hypergradient descent on it. So I discussed several strategies, such as the implicit differentiation, which does not take advantage of the iterative one, some risk estimation through the sugar, or the direct Jacobian estimation at the end of the talk. So thank you for your attention. If you are interested, you can look at several papers that we wrote on the subject, okay, as listed here. Thanks.